that two-dimensional shape is rotated about an axis, which you just saw me do. Those of you who are watching the video didn't see it, but I can show you when you get back. Consider the flat region below to the left. When we take that and rotate it around the x-axis, it gets this shape. The objective of this lesson is to learn how to find the volume of such a solid. Now, there are a couple of different ways of doing this. The first thing that we're going to do is imagine slicing the solid into individual discs of a height 1 unit. The volume of one of those discs will be found by pi r squared h. Because what shape is a disc?
A circle?
A circle, but it's got a height of 1, so that makes it a cylinder. If you cut, it's not flat, it's got a height of 1, so it's a cylinder. And this right here is the formula for volume of a cylinder.
But
Yes.
would that be inaccurate? Because if we're making a smooth surface.
Okay. Yes. Yes. Right now we're just to start with, we're finding them with a volume with a height of 1. But what do you think would make it more accurate?
0.1.
Yeah. The smaller the height, the more accurate your disc. The thinner your slice, the more accurate your answer will be. Just like with Riemann sums, it's the same principle. When you divide those areas up, the area under the curve, the smaller you make the height between your trapezoids or whatever, the more accurate your answer is. Okay, so then what you do is you take all of the discs and you add them together. So sum of all discs, that's the integral between, with the interval being a to b. The a and b come from the same place that they came from a minute ago. That's the beginning of your figure and the end of your figure. So points of intersection, if there happen to be points of intersection. Pi f of x minus the axis of rotation. Now the reason for that axis of rotation thing is this particular shape is rotating right about the x-axis. It's touching it. So there's just a tiny little minuscule dot all the way down the center of the volume where the axis is. But we could actually put a gap in it and rotate it around, and so we would have to subtract out that core. Does that are you following what I'm saying?
No.
Okay.
Well, I think I know what you're trying to say, I just don't get what you're saying. Yeah.
Okay.
Imagine putting a straw in the middle of that.
Yeah,
Solid
okay,
straw.
exactly.
Yes, that makes
So
sense.
if I was to rotate just right around,
X-axis is right in the
I
center.
want to.
I have a
You don't
straw.
have to, you just can't.
Just put the string.
That's what I was going to say, is if this was my, it's kind of frayed. If this was my x-axis, then I wouldn't get the entire, there wouldn't be a big hole like that. It would be really close and very tight around it, just a tiny little hole
Around
where
the
the x-axis just stuck through there. But I didn't. I actually probably rotated it around 2 or something like that. It'll make more sense, and I'll give you more visuals. All of the ones that I showed you had a hole in the center.
Yeah.
They were rotating around something beside. They were rotating about the x-axis, but not on the x-axis.
Why?
They all had a hole in the middle.
I like those questions.
1 or 2 or something like that.
Why do they have a hole in the middle? What's the reason for that?
So you can put stuff in it like a bowl or a cup or a.
Do you mean
Or a
in real
pipe?
life? Do you mean in real life do they, or
Why are they
mathematically
that?
do they?
Mathematically.
Because they're not rotated right about the x. I wish I could draw, but I can't. So if this is not going to have a hole, because as soon as I start to flip this, it's going to be. Can you?
I get
So
what
you
you're
draw it
saying.
from the side.
Well, I can't.
No, I kinda get
I
what
think
you're
I'm
saying.
doing the concept
Wait,
of it.
let me see if I can get one on the.
The thing about
So,
this
like,
is real world.
Here's like your front side of it, but pretend you're looking at it from here and you're looking straight on. So like that right there, that's what you see. So it's touching the x-axis and it's rotating around it.
Okay, here.
How
I'll
far
show you.
it is?
I'll show you. I'll show you. This graphic is a good one.
How far it is from the x-axis?
Yeah.
Okay,
How?
look, I'll show you.
what it's
Here,
doing.
let me show you this one. This is a good example. Because look right here, this dotted line is my axis of revolution. Now watch what's going to happen to my shape. When I hit revolve, it has to go all the way around that axis of rotation.
Yes.
So that's why there's a hole. Now, if I change my axis of rotation, I think I can drag this. Now when I do it, the hole gets smaller.
Yeah.
Okay.
I see what you're saying.
Like, I understand what it's doing, but
And then if I put it right on the x-axis, there shouldn't hardly be a hole at all.
It's just like rotating around like a point, essentially.
Exactly.
Yeah.
So that would be like a solid disc. Now, it would have a teeny tiny little hole right in the center, which would be the x-axis.
What determines your axis of revolution?
You, or the
Okay.
problem.
Yeah, okay, so it's like x equals or y equals, now this is.
Right, and
Okay,
we'll
that
we'll
was my
have
question.
problems that are different.
That's what I figured.
So
That makes sense.
obviously,
That makes sense to me now.
if I was talking about a spool of thread, it is important how wide the little hole in a spool of thread is, because it has to fit exactly on the top of the sewing machine. If it's too big, I don't have my sewing machine there anymore. It would wobble and eventually fly off. So it has to be the right size, so pretty small. Same thing for toilet paper roll. Can't be too small or it won't fit on the little contraption that you have in your bathroom, right? So they're determined by what exactly you need the hole for. And solids like this, look, I don't even know what that might be. But,
Speaker, a vase.
well, I was about to say, it looks to me like something that would generate sound.
It looks like the sound thing on your phone when you're trying to.
It does, it kind of looks like the bell of an instrument or something like that.
Yeah.
Hole needs to be different, bigger, smaller, depending on what exactly it is that your shape is going after. So that's where this axis of rotation comes in. And they'll give you that, you'll either have the information or you'll figure out the information, you'll know if it's supposed to have an axis of rotation or not. Okay, so this says, notice that the axis of rotation is the x-axis and the bottom of the function of the region is also the x-axis. Imagine for a moment what the solid would look like if the axis of rotation were still the x-axis, but the bottom of the function of the region was the line y equals c. They're showing you a picture of this right here. So this is exactly what I just did. So the actual shape is this. It doesn't include this. And you rotate it around so you would end up with a core down the middle. A hole.
okay.
That makes sense.
Okay?
Yeah, I'm seeing it. We're
All right.
going places.
Oh.
So, in order to do this, we must use the formula below to find the volume of such a solid. Outer function minus axis, inner function, just like we did before. It's the two functions, you subtract. The outer function is defined by the function that is farther from the axis. Okay, start there, Mark.
Alright.
I understand it better, like, if you change it in that last thing, because, like, that's what's rotating.
Right.
So I'm seeing it better.
So what this means is there's not equation.
I literally just went to my calculator and calculated that zero.
Oh, yeah.